Okay, hi everyone. Welcome back slash to my channel. I'm Ansar, your helping hand. Dun, dun, dun. Yeah, so in this video, it's a proof video. We're going to be showing that taking a standard normal and squaring it gives you a chi-squared with 1 degree of freedom. Specifically, we're going to be showing it using the CDF form, or using the method of distribution functions. Yeah, so let's just quickly go over some prerequisites that you kind of need to know. So the first thing is you need to know that the standard normal, you need to understand how the CDF, the method of CDFs work, or the method of distribution functions work. So basically, if you have some A and it's distributed with some distribution, D0 for instance, and you have another distribution that's distributed with D1, then if you can show that the probability that A is less than small a is the same as the probability that B is less than small b, for all B's, for all A and B's in the real line, then that means that you have shown that D0 and D1 are the same. So basically, all you're showing is that if you can show that the distribution function of, or the CDF of A is equal to the CDF of B, then you can show that the CDFs, then you know that the distributions are the same, basically. Okay, that's the first prereq, and there are probably going to be a lot more later that I forget to explain. One thing we might want to do is just look at what the CDF of a or the PDF. Well, so the method of CDFs uses distribution functions, but if you take the derivative of on both sides, so if you take dAp of A is less than A, right, that's equal to the PDF of A, so FA of A, and dB, small b, probability that B is less than B, that's the PDF of B, right? You're also doing the exact same thing. You're just working with density functions rather than distribution functions. And yeah, so basically that's the same thing. You're just working with density functions instead of distribution functions. So because we're dealing with the normal and the chi-square, we might want to look at what each of these formulas are. So if z is normal 0, 1, right, then if big Z of small z, so that I usually subscript a lot of my functions with a capital letter that refer to the random variable that I'm talking about. So this is 1 over 2 pi all square rooted e to the minus z squared over 2. Yeah, I think, yeah, that's it. So that's the PDF of Z. If we want to get the CDF of Z, there's not a closed form solution. In other words, there's not a formula that you can write. Well, technically you can write one, but you'll just be writing an infinite number of terms. But there's not one that you can write easily in terms of Z very quickly, where you're not writing forever. So instead, what we say is FZ of Z, right? So this is the cumulative distribution function. We just call this phi. So there's this thing of Z. So essentially, this is just, you're evaluating the integral of this thing, and you're taking the PDF and you're integrating it for a particular Z value. Okay, actually this should rather be like an x and an x here, and you're evaluating it at z. So that's just the cumulative distribution function of z. And then lastly, the last prereq I think that we need is the PDF of a chi-squared. So if v is a chi squared with 1 degree of freedom, then we need to know what the PDF of V is. And we can do this multiple ways. You can either look at what your PDFs are. You can go and look at the back of your book. You can use a gamma distribution, but essentially this is equal to, well, if we use it as a gamma distribution, I'm actually just going to write the PDF. I'm going to assume that you know how to get it. E of V over 2 of the square root of 2 pi V. Okay, so that's F big V of little v. Okay, so that's the the density function of a chi-squared. And I think at this point we now have everything we need. Okay, so I'm just going to zoom out a little bit and move over here. Okay, so we need to prove, so you'll see I do most of my kind of proofs in a very specific way. So before we have that, let's just say what our kind of assumptions are, or what we are assuming to be true. So we're letting Z be standard normal, 0, 1. Okay, so that's the only real assumption we have. So then we need to prove that, let's say, Z squared, we need to prove that Z squared is chi-squared with 1 degree of freedom. Okay, so by the method of distribution functions, this statement of proving that these two things are equivalent, or that not that they're equivalent, but that Z squared actually has this particular distribution, by the method of distribution functions, this is the same thing as saying, proving that the probability that, let's say, Z squared is less than little z, I guess, is equivalent to the probability of, let's say, V being less than little v for all Z and V in R, and we're assuming that V is chi-squared with 1 degree of freedom. Sorry, 1 degree of freedom. Okay, so this whole thing, this this over here, it's not super important. It's just, and what I'm trying to do here is show you what we are trying to prove and how, or what the equivalent statements are, basically. So if you can prove this, you have proven that, basically. Okay, so and also by the same token, the derivative of this with respect to Z, that whole thing is equivalent to the derivative of that with respect to V, where that whole thing is true, and we have the same kind of, criteria or qualifications. Okay, so let's start off with the right-hand side. So the right-hand side is, I'm going to do the PDFs rather than the CDFs, but you'll see that the CDF kind of makes an appearance. So we're doing the PDF of a chi-squared. So the right-hand side is the derivative with respect to small v of the distribution function of v, which is just equal to fv of v, and we wrote it earlier what that is. That is equal to e to the minus v over 2 over the square root of 2 pi v. Okay, so that's the PDF of a chi-squared with 1 degree of freedom. Now we need to go and write what the PDF is of a normal distribution is. Well, before we get there, let's start talking about what the probability that z squared is less than some z, right? This is equivalent to taking the square root of that, so taking actual z and putting it between square root of z and negative square root of z. Okay, so this is just working with inequalities. Once again, I'm assuming that you have a good grounding in algebraic manipulation. But now, if we look at the following, right, this is just equal to the probability that some, remember what z is a standard normal, right? So this is just the probability that some standard normal is between two values. Now, this is equivalent to evaluating the CDF of z at these two bounds, but you can also think of it as doing this, minus square root of z to positive square root of z of the PDF of z, right? With respect to, I'm putting an x here because the x is the x is a dummy variable. Essentially, we don't really care about it. It's just telling us like what our independent variable is. So we're just doing that basically. This x is this value over here. Okay, so this is the same thing using manipulation of integrals. We can say that this is the same thing as taking the integral from minus infinity of square root of z of f z of x dx and subtracting the integral from minus infinity to negative square root of z f z of x dx. Now we can see where the CDFs of z come into play, because this over here is just the CDF evaluated at the square root of z. And because we know that z is a standard normal, we can just use the formula for a standard normal CDF. So this is phi basically evaluated at square root of z minus phi evaluated at negative square root of z. Okay, now we need to manipulate this a bit. So this square root of z and negative square root of z, right? If we think about a normal distribution, right, we need to remember that it's symmetric about 0. So it's symmetric about 0 because it's the standard normal. So what that means is if we take, remember the CDF is basically, the CDF is if I have some, let's say I'm going to call this A, right? The CDF or FZ of A, which is the same thing as phi of A, right? That's telling me the probability that I am less than this particular value. But, or let's call it negative A. So negative A, right? This is the same thing as, hey, what's the probability that I am greater than A? So what we can do then is basically we look at the entire, we look at the entire area under this curve, right? So the entire area under this curve is 1, okay? And if we want to evaluate a particular, if we want to evaluate a particular integral, we can basically work with this symmetric relationship and the fact that we integrate to 1. So for instance, if we want to get negative a, phi of negative a, that's the same thing as taking the 1 and minusing the probability of being greater than negative a, right? That's the same principle. And in the same vein, we can do the same thing here with negative square root of z. So this is kind of just properties of the normal distribution that because I haven't done properties of the normal distribution in quite a long time. We do it, in PTS 144, 114. It's been a while. So this is basically equal to 1 minus phi of square root of z. Okay, so remember the square root of z, right? If we think about this particular little equation over here, right, phi of square root of z is, there's this value over here, okay? So this is z, okay? So we're looking at phi of z is this probability over here, correct? Now, if we want, we can look at negative z, right? And now negative z is this probability or this area over here. Now, what's important to realize is that the area over here, right, is the same thing as this area over here, okay? So, alternatively, this area over here is the same thing as this area over here. So, if we want to calculate what this area is, phi minus z, right? That's the same thing as taking 1, or if we want to evaluate, if we want to evaluate this phi of minus z, it's the same thing as taking the whole area under this curve, right, which is equal to 1, and subtracting the area that's not in this little region over here, which is this area over here. So if we subtract this area, we're essentially taking 1 and subtracting this area, which is phi of z. So that's kind of where this relationship comes from. Doing some more algebraic manipulation, this is phi of root z minus 1 plus phi of root z. So now we have 2 phi of, root z, and we subtract 1. Okay, so that's the cumulative distribution function for z squared. So essentially, if we want z squared and we want the cumulative distribution function for a particular value, we take that particular value and we square root it, we plug it into the standard normal CDF, multiply it by 2, subtract 1, and that's the probability that your z squared will be less than the value you plugged in. So now, if we want the PDF, right, which, if I remind you, the reason we're doing this is because the PDF of this thing, which means the derivative of this thing, should be equal to this this function over here, which is the PDF of a chi-squared with 1 degree of freedom. So the left-hand side of our proof, remember, the left-hand side is the derivative of the function. So the left-hand side is the derivative with respect to z of the probability that z squared is less than z, which is the derivative dz. Sorry, let me just zoom in a bit so you can see better. So this is the derivative of 2 phi of root z minus 1. And then all we have to do is use our derivative laws. So this derivative, that minus 1 is a constant, it's going to go to 0. The 2 is going to come out, and we're going to get dz of phi and square root of z. Okay, now I'm running out of space. So I'll move somewhere else, but I'll actually move somewhere else now. So we have the left-hand side is equal to 2 dz of phi square root of z. Okay, so we need to take the derivative of this function. Now, we don't have the function in terms of z, so we can't just put a derivative there. We have to use the chain rule. So it's going to be equal to phi times, or the derivative of phi evaluated at root z multiplied by the derivative of, with respect to that thing of, with respect to z of that thing. Now, I'm not going to evaluate this yet. I'll just leave it there just to get this out of the way. That's going to be 1 over 2 root z, I'm assuming that you have knowledge and good knowledge or good grounding in your derivatives. But now the important part is this thing over here. So the derivative of the standard normal CDF is just the standard normal PDF, and we're evaluating it at square root of z. So this is going to be equal to 2 times well, we need to have the standard normal PDF. So this is 1 over root pi, 1 over square root of 2 pi, multiplied by e to the minus, and usually we would have something squared over 2 here, but remember we're evaluating it at the square root of z, so when we take the square root of z and square that, that's going to be equal to just z over 2. And then we multiply by 1 over 2 root z, and some awesome things happen. This 2 cancels with that 2. We are left with e to the minus c over 2, and we are left with all of that over root 2 pi z. So this square root and that square root, you combine them. And if we look at this, right, which is our left-hand side, and we look at our right-hand side, we'll see that actually these two things are equivalent if we set v and z equal to each other, which is okay to do, because those v's and z's are just basically those are the independent variables that we're plugging in. So I can just say let z be v, and then this is exactly the same thing. So this is equal to the right-hand side, and so therefore, that implies that z squared is a chi-square distribution with 1 degree of freedom if we assume that z is normally distributed with 0 and 1. Okay, so that brings us to the end of the proof. Please remember to like and subscribe. If you have any questions, put them down in the comments below. If you have any requests, let me know as well. And then, I will have the PDF of all the proofs so that you can look at it rather than going through this entire video. But I hope that just going through the video helps explaining things and I didn't leave anything out. And then you can just refer back to the PDF when you kind of want to, memorize the proof for whatever reason. Okay, cool beans. Bye.